is a little bit more specific. Okay. What I mean by specific is, what is the probability that you win the lottery? The probability you win the lottery. And what is the probability that you win the lottery given that someone on this Zoom call has won the lottery? Okay. So if it's what is the probability that you win the lottery, that is going to be something like 1 times 10 to the 7th, because it'd be that would be like 1 times 10 to the 1 over 1 times 10 to the 7th. It's like how one ticket out of all of the tickets maybe has won. Sometimes no one wins the lottery. So it's very, very, very low probability that you're going to win the lottery. However, if I say, what is the probability that you win the lottery given someone on this Zoom call has won the lottery? Well, currently there's 3 people on the Zoom call, so that would be 1 out of 3, which is a significantly higher probability than before, because before it's like 1 ticket out of all of the tickets printed wins, and the other one is it's just out of people, so it's significantly higher. This bar here that I wrote, this is the phrase given that. Given that this happened, what's the probability? So given that someone on the Zoom call won the lottery, what's the probability that you won the lottery? So that's that bar, given that. And then before we just have whatever we were looking for, the event itself. That's what we were doing here. This is just the regular event. And here is the event, but this is the condition, and we'll call it F. The condition F has already happened. So we don't take everything out of the sample space anymore, not with conditional probability. Then we take it out of for the condition. Demetrius can't hear or see anything. Well, I don't know, Demetrius. Michelle, can you hear or see anything?
I could see your screen and hear everything.
Yeah. Okay. Sorry, it is working.
He may have to log back. He may have to log back in.
Yeah, that's what I told him. Okay. So that's the idea with this conditional probability. Now, conditional probability has a formal definition, and that is the probability of event E given that the event F has occurred is equal to the number of ways that they could happen at the same time, E intersect F, over the number of ways that the event F could occur. Yeah, so this is the formal definition. Okay, we're going to use that definition and some examples to understand how we might do that. Okay, so here's an example. This one's a little bit abstract, but it's similar to the homework. Say we have the sample space of A, B, C, D, E, F, G. we have event E is equal to B, E, G. And we have event F is A, B, D, F, G. Okay, let's find the conditional probability, the probability that E given F has occurred. Okay, so by definition, that is the number of things in E intersect F over the number of things in F. That would be the probability. So let's see, what do they share? Let me get a different color. This color. B, I think they share a B. E, they do not share an E. G, they seem to share a G. So I think there's two things that they share. Then how many things total in F? 1, 2, 3, 4, 5. So this would be 2/5. That would be E given F. Okay, that's E given F. And just by contrast, what is the probability of E? That's the number of things in E over the number of things in the sample space. Again, this is our definition of probability. There's 3 things inside this E, this event, and there are 1, 2, 3, 4, 5, 6, 7 things in the sample space. So the probability of event E is 3/7. The probability of E given F is 2/5. And hopefully we can see that 2/5 is greater than 3/7. Okay. So that's kind of an abstract idea. But that is the general idea. I'm going to take this one off for room's sake. And I'm going to add another one, maybe a different color, so we can keep track. I want to show you that F given E is not necessarily the same probability. So F given E is the number of things in F intersect E over the number of things in E. Okay, well, what they share is the same. It's still the same 2 elements. So that's still 2, no difference there. But the number of elements in event E is 3. And so here we can see that these 2 numbers are not the same. These are not the same. So we have proven that event E given F is not the same thing as the probability of F given E, even though they do share the numerator. So they share the numerator, but they're not the same probability. So that's important that we notice that. Generally, that is true. There are some examples where they could be equal, but generally they're not equal. So it's important that we notice that. And I will say not always, but usually the conditional probability, for instance, 2/5 is greater than 3/7. Conditional probability is usually much, much larger than the actual just probability of the event. So that's something to keep track of as well. Okay. Any questions on that one?
No, that makes sense.
Okay, good. And that's probably the most abstract one we will do until the homework, where there's a few like that. Let's roll yet another 10-sided die. We've done this before. 10-sided die. We're back to the 10-sided die. We want to find the probability that a number is greater than 7, given that it's an odd number. Okay, and I need to state how many times do we roll this? Just once. So let's roll it once. Okay. Let's see. So we have 10-sided die. What's the probability that we roll a number greater than 7, given that we've rolled a odd number? Well, out of 10-sided die, what is n greater than 7? That would be 8, 9, 10. That would be my only options for that. That would be that set. And then the odd numbers out of 10, and we assume there's no 0, right? So 1, 3, 5, 7, 9, and that's it. Okay. So this can help if you, not just you, Michelle, but everyone faced with a conditional probability. If you're confused, sometimes it helps to break things down into pieces and see what you know, what you don't know, and sometimes that's a good strategy. So we need to find the number of elements that fulfill both conditions, which are greater than 7 and odds, and we need to find the number of odds. Okay. Well, we've kind of done this. So what do they share? It looks like they share a 9. And that's it. That's all I see. So it would just be the number inside the set 9. And then how many odds are there? 1, 2, 3, 4, 5. There are 5. So I think this would be 1/5. Okay. Kind of a silly problem, but it is a good lead up to the homework. There's problems like this inside the homework. But conditional probability, well, we're having some kind of guarantee. Again, in case it's not clear, this bar right here is saying given that. Okay. What is the probability that the number is greater than 7, given that it is an odd number? So we're guaranteed it's an odd number, and then we're just trying to find what's the probability of rolling a number greater than 7. Okay. If it was greater than or equal to 7, well, then this would have changed. This would have changed, and I guess we could do that problem too, since I brought it up. What's a good color? Maybe pink's a good color. Let's try the probability of n is greater than or equal to 7, given that the number rolled is an odd number. Okay, well, how many numbers are 7 and above and odd? That's just going to be 7 and 9. That's the only addition to the set. Oops. And the amount of odd numbers has not changed. So I claim that that would still be 5. So this would be 2/5. So if the problem said greater than or equal to, you could do that way. You could also imagine doing less than or equal to, anyway, but this gives us a little idea of how we can talk about rolling die. Let's do another example where we are, we have balls. We have 3 balls. We're going to choose 3 balls. Michael still has his balls out there. We're going to choose 3 balls. Yeah, he's still out there. He's in the homework again. Our old friends are back. We still have Paige Turner. Paige Turner's still out there. Michael still has his balls. James is still struggling in math and biology. Everybody, all the usual cast is back. So we have 3 balls in an urn. Let's say we have 3 green And we have 4 red. Okay. And we want to know the probability that we choose all red, given that we got the same color. Okay. So we're going to choose 3. We have 3 green, 4 red. We want to know the probability of all red, given that they're the same color. Okay. Welcome, Dylan. We're talking about conditional probability. Okay. So let's see how we can do this. Well, we need to find the number of ways we can choose all red and them being the same color over the number of ways we can have the same color. Okay, so that is the idea of this problem. Now, this will happen a lot in this type of section. Oh, this is Demetrius. Welcome back, Demetrius. So it's the numerator is kind of redundant. And that happens a lot in these problems. So it says the number that are all the same color and they're all red. Well, if they're all red and they're all the same color, that's the same thing. So we're really just talking about how many ways can you do all red. So that's a redundant statement, and that happens a lot. And we still want to do same color. Okay. Now we're choosing 3. We have 3 green, 4 red. I hope it's clear that we do not care about the order of these things. I don't care the order of choosing red balls. I don't care the order in which they come. I just care that how many I get. So I'm going to use combinations to solve this problem. So how can I choose 3 balls and out of 4, I claim that would be 4, choose 3. I don't care what order, but I think there's 4 ways to make groups of 3 with 4 things. So 4, choose 3. And then how can you do it with the same color? Well, this is a little bit more annoying because you could have all green, and that would be 3, choose 3. Or you could have all red, which is what we're trying to find the probability for. So let me write down what I just said. This is all red, and this is all green. Okay, but it just said, so our sample space is just the same color. So we have to worry about both cases. Okay. So from there, it's just arithmetic in our way, and we should be able to find it. 4, choose 3 is 4. 3, choose 3 is just 1. And 4, choose 3 is 4. So I think this is going to be 4/5. I think that would be the probability. Any questions on that one? So this will happen a lot in this chapter, in chapter 4, where you have a denominator where it has multiple scenarios that you have to kind of piece together. So that is something to look out for. But yeah, if there's no more questions, then I'm going to define something else that we need for this section, and that is the idea of independence. Okay. So 2 events are independent if and only if the probability of their intersection is the same thing as the probability that you multiply them. This is the definition of independence. It doesn't mean any more and it doesn't mean any less. Okay. This gets confused a lot with disjoint sets. And in fact, it got so confused that at least we had a break in between defining what a disjoint set is. It used to be taught pretty close together, and that was part of the problem. But this has no relation to disjoint sets or partitions. Okay, but that's often confused, and hopefully it's not confusing because we have a little bit of a gap between when we learn those things. But this is the definition, that the probability of their intersection is the same as multiplying their probabilities. Now you can see it's not going to have a lot to do with disjoint, because disjoint means that their intersection is zero. The probability of their intersection is zero. So that means one of these would have to be zero for this to work out. So I wouldn't, I mean, maybe it's going to get, maybe it's one of those, what do they call it? The Barbra Streisand effect, where I keep saying it doesn't have anything to do with disjoint sets. And then you guys will think it has something to do with disjoint, it'll backfire. But that's the idea. That's the idea that, um, of there. So it doesn't mean anything more or anything less. We're going to see some word problems, examples. Right now, I just want to show the most abstract way I could possibly do. Let's say that the probability of event E is 50%, and the probability of F is equal to 50%. And their intersection is E given, or I'm sorry, E intersect F is 1/4, and we can test if E and F are independent. Okay, so let's see if they're independent events. The way to test this would be to simply multiply them. So it says that their intersection is the same thing as multiplying them. And so let's see if that's true. Their intersection is 1/4. The probability of E is 1/2. The probability of F is 1/2. If I multiply these two numbers, I get 1/4 equals 1/4. So yes, they are independent because they fulfill that definition. Okay. It doesn't mean any more or any less than that. That's how we're going to define the probability, or the improbability. That's how we define the definition of independence. So let's say we have the probability of G equals 1/8, and the probability of E intersect G equals 1/7. Are these independent? Test if E and G are independent. Okay, let's see. So by definition, that would be E intersect G equals the probability of E, and it doesn't matter which way you multiply them, that doesn't matter. Let's see if this works. So 1/7 equals, E is still a half, G is an eighth, so 1/7 equals 1/16. No, that's not true. No. These events are not independent. Okay. it might not make sense what the word independence means, but does it make sense how I'm using the formula?
Yes, we're just plugging and chugging.
Plugging and chugging is really all I'm expecting at this moment in time. Um, I'm not laying anything about word problems or anything like that right now. And honestly, I feel like for this class, it's probably best to just leave it like that, just to think of it as a formula and not to try to add any meaning to it. But we can always go back. We can go back to Michael's balls here, and we could see if the probability of a green and the probability of a red is independent. We could test that. Let's see. Let's test. So test if green and red are independent. Okay, let's see. So the probability of a green, well, there's 3 of them, and there's 3 out of 7. So there's 3 sevens. The probability of a red is 4 sevens. What's their intersection? How many red green balls do we have in this problem?
7.
How many balls do we have that are both green and red?
Oh, none.
0 out of 7, 0. So let's test to see if this works. The probability of green and red equals the probability of green, probability of red. Well, that's going to be 3 sevenths times 4 sevenths equals 0. That is not true because that would be 12/49ths, and that does not equal 0. So these are not independent. Okay. So does that make sense? I mean, that's the definition. So does it make sense?
Yes, sir.
Okay. So, my thought of independence outside of finite class might be that the red balls don't have anything to do with the green balls, right? You could say, well, they're totally free to do whatever they want. But we can see with the probability in this scenario, that's technically not true. They are not independent. Those events of drawing a red ball in this scenario is not independent of a green. They are tied up together. They are dependent. They are dependent of each other. So that's confusing, especially in this class because we just kind of touch on independence. If you take we'll have some practice in the homework too. We'll look at that. But it can, honestly, I feel like my strongest suggestion is to just take it as another formula and just say this is independent, this isn't independent, and don't try to add any meaning to it. That's usually what trips people up. And sometimes the writer of IU exams can be really mean, and they can actually they'll write something like they're independent events, and they don't mean the same independence. I've seen that before, and that's, I think, kind of harsh to do to students, but that's what they do. Okay, that's, I think, all the definitions we need for 4A. We really only need to define conditional probability and what an independent event is. Independence. That's the only 2 things we have to define. So